Now, in the last video, we had talked about an object moving, and it was moving solely under the influence of gravity. And so this is what we call projectile or ballistic motion. So the operating thing here is that it's only moving under the influence of gravity. So what kind of motion is it? This is actually an interesting thing. Historically, Galileo Galilei looked at this projectile motion thing, and he realized some of the ideas they used to have were wrong. For example, they used to think when you shoot a projectile, it would go and you'd throw it and move in a straight line, then fall. You shoot a little farther, fall further. Now, in Galileo's time, they were actually starting to use gunpowder, and one of the issues they ran into was that you had the enemy would build small walls and take position behind it. So you have a cannon, and you put a shell in it and a certain amount of gunpowder and throw it a certain distance, put more to throw it farther. And so they thought you put a little bit more in there and throw a little farther and fall on top of them. Except that's not what happened. What they found was, the first one hit here, then hit here, and the next one, instead of falling there, would hit further up here, and then they put a little gunpowder in it. Instead of landing just behind here, it'll land over here. So there's actually a region here where they couldn't hit. And so they were trying to figure this out, and this is when Galileo comes in. And he says, well, let's look at it. And he did this, the hard way, because he didn't have the modern vector terminology. But we say that we can derive it a little easier than he did it. The initial velocity is like this. So that means we have an initial x velocity, which is going to be v naught cosine theta, and initial y velocity, which is v naught sine theta. Okay. And so this is the initial x and y components. And so he says, okay, what we've got here is we know that we know that y is going to be equal to y naught, and again we'll say that x naught and y naught are 0. So this will be vy naught t minus 1/2 gt squared. And then x, and you realize that the acceleration was only in that direction. And so that means that x is just going to be vx naught times t, because x naught is 0, and then the x acceleration is 0. So he looks at this and says, oh, wait, t equals x over vx naught. So x is however far it goes. And then vx naught is given by that. Okay, so he says if I plug that in, then what we've got is that y. So what we've got is that y equals vy naught times vx naught, divided by x times x divided by vx naught minus 1/2 g x over vx naught squared. And so you look at this and you find that vy naught over vx naught times x minus 1/2 g over vx naught squared times x squared. Okay, so y equals ax minus bx squared, where that is a and that's b. Okay. Well, wait a minute. This is the equation of a parabola. So that means that what was happening was that the shell would go like that, okay, and then you put more powder like this, more powder goes like this, more powder does like that, more powder does like that, and that's why there was a region behind the wall they could never hit. And so it's parabolic motion. So that was a first step forward as to how projectiles work. So then he started looking at it and said, well, wait a minute, what is the maximum height? So I want to know what is y max. Okay. And so, well, we say, well, how do you find, we know that y equals Vy naught t minus 1/2 gt squared. Well, how do you find the maximum of a function? Take a derivative and set it equal to 0. So that means that dy dt equals Vy naught minus gt. Well, wait, and set that equal to 0. Now, wait a minute. That is actually just Vy. So it's going to be maximum height when the y velocity is 0. Now, it's important. The velocity, the total velocity, is going to be Vx squared plus Vy squared. So Vy0 does not mean that the velocity is 0. What it means is that the y velocity is 0. So it still has x velocity, so it didn't stop up there. Likewise, the acceleration is not 0. The acceleration is g the entire time. So we set this equal to 0, and we say that t is just going to be equal to Vy naught over g. Now, if I plug that into this equation right here, so y equals Vy naught times Vy naught over g minus 1/2 g Vy naught over g squared. And so that means that if we do a little bit of algebra, this is going to be equal to Vy naught squared over 2g. So y equals, plug in for what Vy naught is, V naught squared times sine squared theta over 2g. Okay, so what does that mean? Well, this is y max. So the maximum height. So you throw something and you want to go to maximum height here. What's the highest you want to go? There's several ways of doing that. One is that you could change V naught. You could actually shoot it at a faster velocity and it's going to go higher. Well, yeah, you shoot a basketball. The harder you throw it at a particular angle, the higher it's going to go. Okay, the angle matters. Okay, so it's going to go highest if sine theta is biggest. Well, the biggest sine theta can be is 1. That would be if sine is 90 degrees. So what would happen is if you shoot it straight up, it's going to go higher than if you shoot it at an angle. Ideally, shoot straight up, it goes the highest and comes back down. Again, he started this whole stuff with artillery. If you want your artillery round to go higher, you shoot it straight up. Problem is, that means it falls straight back down. That's one of the problems with anti-aircraft artillery. World War II is that if you have very high-flying aircraft, then you have to shoot almost straight up, but that means the shells come straight back down, or they explode and then the shrapnel comes straight back down. G. You can't control G, but if you were to shoot at on another planet with lighter gravity, it'd go up higher. And you obviously can't control 2. Okay, so next question that he asked was, what's the farthest range? So what is the farthest? You want to shoot it the farthest. And so how do you do that? Well, so you want x. We know that x equals Vx naught t plus 1/2 ax t squared. Well, the ax t squared is 0, so x is just going to be Vx naught t. Okay, and so you wanted to go farthest possible. Well, you cannot take the derivative and set it equal to 0 because this is not really an extremum of the function. If the ground was not there, it would have kept going. And so the strategy of taking derivative and set it equal to 0 does not really hold in this case. But we do know that this is a boundary value problem, meaning that we have another condition here. We say it stops moving when y equals 0. Well, y equals Vy naught t minus 1/2 gt squared. So I can factor that and say this is t times Vy naught minus 1/2 gt. Okay. And so we look at that, we say, okay, that's 0. If this is 0, that's when you start, t equals 0. it's also 0 when that is 0. So that would be 0 when t, we just do algebra here. We set that equal to 0. And so that would be 0 when t equals 2v(y)0 over g. So we plug that into here. So x max occurs with vx0 times t. T is 2v(y)0 over g. Okay, so this is 2vx0 vy0 over g. Well, now let's plug in for what we know about vx0 and vy0. So that's 2 times v0 cosine theta times v0 sine theta over g. So in other words, this is equal to v0 squared times 2 cosine theta sine theta over g. Now, way back a long time ago, you needed to learn trig identities. And another trig identity day. This is the day. You need to know that 2 sine theta cosine theta is equal to sine 2 theta. So we can substitute this in, for that, okay, right up here. So x max is now going to be equal to v0 squared sine of 2 theta divided by g. Okay, so I want it to go farthest. What makes it go farthest? Well, if I shoot it with a higher velocity, it's going to go farther. So that would be the v0. If I go to the moon and shoot it, it goes farther. One of the astronauts to the moon was an avid golfer, and he took a little golf head with him and attached it to the end of a rock sampling arm and hit a golf ball on the moon. It went for miles and miles. Well, it didn't really do that because he was in an awkward spacesuit, but it did go longer than it would have if he had hit it from Earth, because gravity in the moon is 1/6 of what it is on Earth. Okay. And also, if sine 2 theta is bigger. Now, again, the biggest the sine can be is 1, and so if that would be at 90 degrees. So 2 theta equals 90 degrees, meaning that theta equals 45 degrees will make it go farthest. So if you shoot a projectile, shoot at a shallow angle, shoot at a steeper angle, okay, it's going to go farther. Okay, it's going to go farther if you shoot at a steeper angle. But if you get steeper than 45 degrees, it doesn't go as far. So this is why in military weapons, 45 degrees, artillery pieces go up to about 45 degrees, and that's as far as they go up, because shooting farther than that makes the round actually land closer. Okay. Battleships in World War II, the main guns would only elevate to 45 degrees because going farther wouldn't make it go any further. The military does have weapons called mortars that shoot at more than 45 degrees, and they kind of drop down, and they're good for going over obstacles and things, shooting over obstacles. So that's what a mortar is good for. Tanks, their main guns go up about, a little bit over 45 degrees to about 55 degrees. And that's because the tank could actually be on a hill and then want to be able to shoot a long ways. But this is the basic idea that you have. Now, the other thing is that because it's a parabola, this end is symmetric with that end. So that means the angle here is going to be the same as the angle there. So the angle that it hits at is going to be the same. Likewise, the velocity here is going to be the same as the velocity there, assuming you ignore air resistance. So for a parabola, this is a symmetric sort of proposition. So, but this is the basic ideas of projectile motion.